Welcome back. In the last video, we mentioned binomial distributions. In essence, binomial events are a sequence of identical Bernoulli events. Before we get into the differences and similarities between these two distributions, let us examine the proper notation for a binomial distribution. We use the letter B to express a binomial distribution, followed by the number of trials and the probability of success in each one. Therefore, we read the following statement as, variable x follows a binomial distribution with 10 trials and a likelihood of 0.6 to succeed on each individual trial. Additionally, we can express a Bernoulli distribution as a binomial distribution with a single trial. All right, to better understand the differences between the two types of events, suppose the following scenario. You go to class, and your professor gives the class a surprise pop quiz, which you have not prepared for. Luckily for you, the quiz consists of 10 true or false questions. In this case, guessing a single true or false question is a Bernoulli event, but guessing the entire quiz is a binomial event. All right, let's go back to the quiz example we just mentioned. In it, the expected value of the Bernoulli distribution suggests which outcome we expect for a single trial. Now, the expected value of the binomial distribution would suggest the number of times we expect to get a specific outcome. Great! Now, the graph of the binomial distribution represents the likelihood of attaining our desired outcome a specific number of times. If we run n trials, our graph would consist n plus 1 many bars, one for each unique value from 0 to n. For instance, we could be flipping the same unfair coin we had from the last lecture. If we toss it twice, we need bars for the 3 different outcomes: 0, 1, or 2 tails. Fantastic! If we wish to find the associated likelihood of getting a given outcome a precise number of times over the course of n trials, we need to introduce the probability function of the binomial distribution. For starters, each individual trial is a Bernoulli trial, so we express the probability of getting our desired outcome as p, and the likelihood of the other one as 1 minus p. In order to get our favored outcome exactly y many times over the n trials, we also need to get the alternative outcome n minus y many times. If we don't account for this, we would be estimating the likelihood of getting our desired outcome at least y many times. Additionally, more than one way to reach our desired outcome could exist. To account for this, we need to find the number of scenarios in which y out of the n many outcomes would be favorable. But these are actually the combinations we already know. For instance, if we wish to find out the number of ways in which 4 out of the 6 trials could be successful, it is the same as picking 4 elements out of a sample space of 6. Now you see why combinatorics are a fundamental part of probability. Thus, we need to find the number of combinations in which y out of the n outcomes would be favorable. For instance, there are 3 different ways to get tails exactly twice in 3 coin flips. Therefore, the probability function for a binomial distribution is the product of the number of combinations of picking y many elements out of n times p to the power of y times 1 minus p to the power of n minus y. Great! To see this in action, let us look at an example. Imagine you bought a single stock of General Motors. Historically, you know there is a 60% chance the price of your stock will go up on any given day, and a 40% chance it will drop. By the price going up, we mean that the closing price is higher than the opening price. With the probability distribution function, you can calculate the likelihood of the stock price increasing 3 times during the 5-workday week. If we wish to use the probability distribution formula, we need to plug in 3 for y, 5 for n, and 0.6 for p. After plugging in, we get number of different possible combinations of picking 3 elements out of 5 times 0.6 to the power of 3 times 0.4 to the power of 2. This is equivalent to 10 times 0.216 times 0.16, or 0.3456. Thus, we have a 34.56% chance of getting exactly 3 increases over the course of a work week. The big advantage of recognizing the distribution is that you can simply use these formulas and plug in the information you already have. All right, now that we know the probability function, we can move on to the expected value. By definition, the expected value equals the sum of all values in the sample space, multiplied by their respective probabilities. The expected value formula for a binomial event equals the probability of success for a given value, multiplied by the number of trials we carry out. This seems familiar because this is the exact formula we used when computing the expected values for categorical variables in the beginning of the course. After computing the expected value, we can finally calculate the variance. We do so by applying the short formula we learned earlier. Variance of y equals the expected value of y squared minus the expected value of y squared. After some simplifications, this results in n times p times 1 minus p. If we plug in the values from our stock market example, that gives us a variance of 5 times 0.6 times 0.4, or 1.2. This would give us a standard deviation of approximately 1.1. Knowing the expected value and the standard deviation allows us to make more accurate future forecasts. Fantastic! In the next video, we are going to discuss Poisson distributions. Thanks for watching.